All right. Last lecture, we talked about some stoichiometric defect reactions, and we're going to pick up from there today in this module. And what we're going to look at is that Schottky defect. And I rewrote it here so that you can see it. So this is the reaction that we wrote. We have a metal vacancy, and this is an MO oxide. So 2 plus, and then, 2 minus, and then 2 plus on the oxygen vacancies. And then those atoms go to the surface, and so we write them like this. And then the null is the the reactant side. And so we can write that a number of ways, but null is the simplest. So everything is in its proper position here. So where I wanted to pick up from last time then is how we define the concentrations of these vacancies. Because unlike simple point defects where it's a matter of, for example, with a vacancy just moving one, here we have a paired combination. So in this case, we have what we term the anion vacancy. So in this case, it would be the oxygen. And then this is equal to the metal, so the cation vacancy concentration. And I'll explain it here in a second, but these are the site fractions or concentrations. And so that's going to be equal to an exponential of the entropy for Schottky defects over 2K, where that's the Boltzmann's constant, multiplied by an exponential minus delta H of S for over 2KT. So again, K is Boltzmann's constant, and then here the S is for entropy, H is for enthalpy, the lowercase denoting we're talking about 1, and then the S subscripts are talking about Schottky. So the enthalpy and entropy changes in putting a Schottky defect into this material, and that's equal to these concentrations or mole, what we call mole or site fractions. And so we define that. So this is the square bracket for the anion vacancy. And so that's equal to the number of anion vacancies over the number of anion vacancies plus the total number of anions. So like this is the total sites, this is the number of anions. So that's the site fraction. And the same definition for cations, but just replacing anion with cation. Right? So it's just the cation or anion vacancy fraction of the total sites. And so we use this square bracket terminology when we're writing these defect reactions as a way of denoting the site fraction. So whenever you see that, think site fraction. Okay, and so we also know that the Gibbs free energy of that reaction is equal to this term. And that's what you see up here. So basically, if you're seeing these two terms, you're basically looking at the Gibbs free energy. Okay, so that's just a little bit more information on the Schottky that we talked about last time. You know, we can write the site fraction of that based on an exponential function of the free energies, and then those site fractions are defined as this. All right, so now let's go ahead and look at another type of defects, and that's the Frankel. So let's look at Frankel defect reactions. So again, this is the pair of vacancy with interstitial. And so for a MO oxide, this is gonna, for a typical one, right, it's gonna be a cation because the cations are smaller. And so we would write that reaction as null or perfect crystal. Goes to, so everything in its proper position, and then the Frankel defect would be a metal vacancy, just like we had before, and then that metal ion goes into an interstitial, and the charge is +2. right? So this is our reaction, and we can do the same mass, charge, and site ratio balance to make sure that it is the same. And again, you could also write the left side here as metal in metal site with no charge, right? Denoting that the metal is in its proper site and there's no issue with charge. So there's a number of ways you can write this left side, so I don't get too picky with that. All right, and so just to reiterate here, we're talking about the metal for the Frankel because the it has to go into interstitial site, so it has to be the smaller of the two. So this is going to be structure dependent. If you're looking at a structure that's not as typical and the anions are smaller, then you would want to rewrite that for the anion. So for example, let's write an anion Frankel just to show that. And so in this case, we're still looking at this oxide. So let's do oxygen in the oxygen site in its normal position instead of the null or perfect crystal. And so in this case, we'd have a oxygen vacancy. In this case, it would be +2 charge. And then the oxygen goes into the interstitial, and that has a -2 charge. All right, so that's how we would write the Frankel defects. So we're just using the Kroger-Vink notation that we learned and putting them together in balanced defect reactions, balancing mass, charge, and the site ratio. All right, so now let's look at another type of stoichiometric defects, that being a misplaced atom. Sorry about the focus there. So here, again, I mentioned this, and in the wording you see that it says atoms, right? So typically we think of ions, but if these are ionic materials, we typically don't see misplaced ions happen because of the charge considerations, right? Because they have to flip sites, and therefore a negative is going to be surrounded by other negatives and positive by other positives. So it's very unfavorable. So this is more common for covalent ceramics, where the electrical configuration and the valence structure is similar between the two types. And so we have a swap of the atoms. So that's what we would see in these cases. All right, so in this case, instead of writing out this myself, I'm going to have you look at an example of this in the next section. So the next section will go through some examples, and we'll look at how we write a misplaced atom in those examples. All right, the last thing I want to touch on in this module is equilibrium constants. So we talked about these for chemical reactions. Now let's look at them for defect reactions. And so just to recall from that section, we had a general chemical reaction like this, written like this, and our mass action expression, our equilibrium constant, was equal to the activity of the components, products over reactants, and raised to their coefficients. So we had something like this. So for our defect reactions, if we assume that it's ideal or ideality, so if these reactions happen ideally, then we're going to replace the activities with mole fractions. So this is similar to in our chemical reactions when we saw that the activity could be replaced with the the concentration, right? This is basically the same assumption we're making, and that happened in the ideal cases. So we're going to replace it with the mole fractions. And so again, let's go back to the Schottky defect, and we have the general reaction as you've seen a couple times now. And if we want to write the equilibrium constant or mass action expression, then we can do it in the same way for this reaction. So these are the products. So it's going to be the vacancy of metal site fraction raised to the coefficient, so just 1, and then the site fraction of oxygen vacancies raised to the coefficient, so 1. And then on the bottom side, again, keep in mind that on this side, null means everything is in its proper place. So we can write that as metal and metal site, and then oxygen and oxygen site. So in effect, this is going to be just equal to the top. Right? Because it's effectively, in this case, the mole fractions of this, if we write this out, right, this is the number of metal ions divided by the number of metal ions plus the vacancies. That vacancy number is quite small, so let me just do that over here. This is equivalent to the number of metal sites over the number of metal sites plus the vacancies of metal, right? But this is always relatively small compared to the number of ions, and so effectively this is equal to 1 because this is so small. So that means this goes to 1, this goes to 1, and we're just left with this. And so it works out just like we see here in that we really only have to deal with the products. But this is our mass action expression for Schottky. And so we'll write similar ones. We can write similar ones for all of the other reactions using the defect reaction that we've written.